Hi, class. Knowing that you guys can always speed this up or slow it down, I'm just going to try to expedite this as quickly as I can. But anyway, before we do example one, all right, we're going to be talking about solving logarithms, solving using logarithms, and solving exponential equations, etc. But anyway, let me just a quick note before we get into this is I just want to show you a couple things that will seem to make sense. If I have something like, I'll give you an example, like 7 to the x equals 7 to the third. I want you to recognize that if the bases are the same, then the exponents must also be equal. We've done this before, and so in this particular case, we would know that x is equal to 3. And I think that seems pretty reasonable. It's also true in terms of logarithms, but if I have a log base 2 of x, let me get rid of those parentheses because that was a problem on the quiz too, I guess. Log base 2 of x equals 7 equals, log base 2 of 3. Let's put that one. Then if it's log base 2 of x equals log base 2 of 3, well, notice that that would also mean that x is equal to 3 because it's the log part is the same, and so the numbers must be equal also. So anyway, that's just a little bit of some thinking that you need to have to go into this next problem. So example one. In example one, what happens is we're going to try to solve for the exponential equation. In this particular case, though, what we're going to try to do is express it as an equation to the same base. So what does that mean? Let me go ahead and make that bigger. But if I can rewrite 1 over 10 as being 10 to the negative 1, and I hope you can convince yourself that that's true, to the x minus 3 equals, and what is 100 as a base 10 number? Well, that's 10 to the what is 100, I should say. 10 squared is 100 to the x, right? So what I've done, one of the things that we're going to be doing is trying to express, if we can, we try to express the equation as having the same base on the left and the right side. Once the bases are the same, the exponents must be equal. So of course I know what I'm doing here, so I'm sure if you looked at that, you wouldn't have thought to do it this way, but this is what you're gonna try to work at. Well, of course, that means the same. This is the same as 10 to the 2x. And if I distribute that negative 1 to here, I get 10 to the negative x plus 3. Why did I do that? It's because I multiplied negative 1 times both of these numbers. So now that the bases are the same, we can set the exponents equal to each other. So this is one of the ways that we solve exponential equations. Negative x plus 3, add x to both sides. 3x equals 3, and so x would have to be equal to 1. Okay. To do the next one, we're going to have to rely on another trick. So I already gave you a couple tricks here. This is I guess this would be trick 1, and this would be trick 2, but trick 3 refers to this idea. If I have log base 3 of 3, and we'll be talking about this a little bit more in a little bit, log base 3 of 3, ask the question, 3 to what power is equal to 3? The answer is going to be 1, x equals 1. Well, it's also true that the log base 10 of 10 is equal to 1. The log base 22 of 22 is equal to 1. So, and we're going to be using that. I'm going to review that again in a little bit. Well, why am I talking about that? Well, the reason I'm talking about that is because on this next question here, what I'm going to do is I'm going to take the logarithm of both sides. Because I don't have the same base, I can't set the exponents equal to each other. So in a situation like that, which is more often than not, this is what logarithms were built for. So what I'm going to do, and in a moment you're going to see why, I'm going to take the log base 2 of both sides though. So if I take the log base 2 of both sides, I get log base 2 of 2x equals the log base 2 of 7. So I can log both sides of an equation. Now, okay, it looks like I wrote that incorrectly. Let me fix that. Sorry about that. That x belongs as an exponent, right? Sorry. Okay, now let's take this x. We're going to use our third property of logarithms, and we're going to take this exponent, we're going to move it to the front. And so we can rewrite this now as x log base 2 of 2 equals log base 2 of 7. Well, look at this log base 2 of 2. If you haven't forgotten what I taught you 60 seconds ago, you're going to remember that that is actually the same thing as 1. So this becomes just x times 1 equals log base 2 of 7, and that is your answer. And you can put that in a calculator and figure out what that is. It should come out to about 2.807. So we go x is approximately 2.807. Okay, well, anyway, so two solving exponential equations. One case where we try to get the base the same, and the other case, if the base can't be the same, we're going to take the log of both sides. Okay, so let's go to solving these equations. These are your practice ones, believe it or not. And I would totally invite you to try to do what I just did in B. Look what I just did in B and see if you can't replicate that for number 1. I'm going to pause right now, and hopefully you have your homework or you have a copy of these notes from my essay that you can do this on, but I'd like you to take a moment and see if you can't figure this out. When you do, unpress pause and see how you did. Okay. Did you get what I got? Anyway, again, I took a log base 2 of both sides because I want to match the log base with the exponent's base where I'm solving for x. Again, taking log of both sides, I can now take this exponent, move it to the front, all right? And that's what I have in the second line here. And now I get log base 2 of 2. Log base 2 of 2 is going to be 1. So 1 times x is just x equals log base 2 of 5, which in your calculator should come out to about 2.322. Okay, let's do the next question. Now, in the next question, we're going to do the same thing. But in this case, what we're going to do is we're going to use the log base 7. Why is that? Because we want to match the log base to the base of the exponent that we're trying to solve the x for. So log, let me go ahead and get you started on this one because it looks a little weird. Log base 7 of 7 to the 9x equals log base 7. Why did I do that? Log base 7 of, what did I do that again for? 7 of 15. Okay, again, bring the 9x to the front. So now I got 9x log 7 of 7 equals log base 7 of 15. Well, of course, this is going to become a 1, right? So now I've got 9x equals log base 7 of 15. Divide both sides by 9. And why am I writing the wrong numbers all the time? And I'm good. Now I've got x equals log base 7 of 15 over 9. And you can stop there. Let's go to, and you could take an approximation. I'll show you how to do that on a calculator because we haven't done much of that. Okay, well the next one looks absolutely totally impossible, but it is doable. And but I want to do it with you because it looks strange at first, and I'm not sure how many of you figured out the first step. The first step is merely to add 7 to both sides. So now I've got 4e to the negative 0.3x equals 20. Well, guess what? We can now get rid of that 4. So it's getting simpler here. It's e to the negative 0.3x equals 5. Now I am going to take a log to the base of the exponent to which I'm solving for, base e. And if you remember, we have we could use log base e, or there's a shorthand version called natural log. So natural log of e to the negative 0.3x equals natural log ln 5. Okay, put the exponent to the front. All right, and I'm running out of space here. Now I've got negative 0.3x ln e equals ln 5. Well, guess what ln e equals? It equals leany. No, it equals 1. So we can write this as negative 0.3x equals ln 5. Now we just divide both sides by negative 0.3. So you get negative 0.3 down to the bottom. And that's it. That's your answer. It looks weird. You can put it in your calculator and get a number. So if this was actually a calculation for finding the size of a part for your space shuttle or your rocket or your computer, you could just go ahead and make an approximation for that in your calculator, and you can just pull that size right out. Okay, so let's go ahead and move to the next our next page. Our next page, I just want to review review really quickly, because we're going to use this a lot in this next one. Is this idea, and I just pulled these out of the book. Log base 12 of 12. Log base 12 of 12 is 1. Log base 4 of 4 is 1. Log base 7 of 7 is 1. Log base 3 of 3 is also just 1. A couple special ones to remember, though, too, is remember that we have two shorthands in logarithmic world. Log base 10 means the same thing as log with nothing written at all. Because log base 10 is so popular, they just drop the 10 off. Anytime you don't see it, you just assume there's a 10. The other one, too, is that the log of the base e, 2.7, blah, 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 whatever it is, has a shorthand version of ln. So just remember that. So in that case, given that means that log 10 equals 1. And the other thing, the stranger looking thing, is that ln e also equals 1. And we saw that. I already alluded to that in the previous one. But we're going to use this. We're going to use this trick in the next two examples to solve some more problems. So let's go to the next page and see if you can remember this kind of cool trait of logarithms. So here we go. Okay. Now the first problem. We have the log of 4x minus 7 equals the log of x plus 5. Well, if the log of, or the natural log of 4x minus 7 is equal to the natural log of x plus 5, then that must be true that 4x minus 7 equals the x plus 5, right? Think about it. Kind of makes sense. They're both being logs, so they must be the same. So with this one, we're just going to subtract, whoopsie. We're going to subtract our x, and we get your 3x minus 7 equals 5, and then you add your 7 to both sides. Can't write. 3x equals 12, x equals 4. Okay, done. All right, next one's a little trickier, but if you remember, let me just show you the trick I'm going to do. This one here, let me go ahead and rewrite it first. Log base 2 of 5x minus 17 equals 3 times, well, I'm going to tell you something. I can write the number 1, or I can remember that there's a fancy way for me to write number 1 based on logs. And what I'm going to do is I'm going to put right in here log base 2 of 2. And I want you to tell me think about why is it that I can just write that down 3 times log base 2 of 2. Does that change the value of the right side? And the answer is no. Why? Because we know that log base 2 of 2 is equal to 1. And multiplying the right side by 1 doesn't change anything. Okay, but what does that allow me to do? It does allow me to take this number in the front and put it up here as an exponent. And take a moment and see how cool what that's going to do for us. And now the problem is very similar to the one we solved at the beginning. Log base 2 of this equals log base 2 of that. That means that this must be equal to that. 5x minus 17 equals 2 cubed. 2 cubed is the same as 8. So you're going to add 17 to both sides, and you get 5x equals 25. X must be equal to 5. All right, so some clever little tricks going on here. And so what I'd like you to do is go ahead and practice these. Now, one of the things, too, they want you to do is to check for extraneous solutions. Whenever we do this problem is very similar to when we're squaring or when we're squaring numbers. We sometimes can create extraneous roots. So let's be careful that whatever answers we have do work inside the problem. Okay, so let's take the first one. First one's pretty simple. Natural log of this equals natural log of that. Well, that must mean that 7x minus 4 is equal to 2x plus 11. Subtract 2x from both sides, and you're going to get 5x minus 4 equals 11. Add the 4. 5x equals 15. X equals 3. Now, one of the things that something we haven't talked about yet is that the log, any logarithm, unaccepted values of numbers that can be logged as anything that's negative, 0 or negative. There's no such thing as log of 0. Really quickly, I can just demonstrate that really quickly. If I have log base 10 of 0 and I want to know what that's equal to, I would say 10 to the x equals 0. Well, there's no value for x that's going to give me 0. And you might say, oh, it's 0, but no, 10 to the 1 is equal. 10 to the 1 is equal to 10 to the 0 is equal to 1, not 0. So it's impossible for us to have a log, a positive log. The other thing that can happen too is I can't have the log of a negative number. So say I have log base 10 of negative 2. Let's see what that's asking. Well, that's asking, instead of saying 10 to the x is equal to negative 2. Well, there's no power that I can bring the 10 to give me a negative number. So basically, in short, what that means is that no value, that I'm not allowed to have any value in the logarithm that's either a 0 or a negative. So when they ask for extraneous roots, what they're looking for is any number which when put into the equation, which when put back into the equation is going to produce a negative number. So let's go ahead and check. We have x equals 3. And so if I go ahead and plug in the 3 into this number here, I do get a positive number for the log. It's going to be 2 times 3 is 6 plus 11 is 17. If I put a 3 into here, it also works. I have 21 minus 4, which equals positive 17. So we're good. No extraneous solutions, all right? Let's go to this next one. This next one, we're going to use our trick again, and that we used above, if you can remember. I would love to challenge you right now to go ahead and pause and see if you can figure this out based on the second problem that we did up here. All right, so see if you can't follow along with this one, and 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 do number 6. I'll pause, and when you unpause, you'll be able to see the answer. Okay, again, we're going to use these same techniques that we were using a moment ago, and let's get started. But on this one, what we're going to do is use some of the properties of logarithms that we've had in the past. Now, if we look at this first example, you'll notice that we're adding the logs. See that up there? Guys, remember what adding the logs was the same as? Watch what I write and tell me, see if you can convince yourself that I'm not kidding you here. So I'm going to write this as, I'm going to take this left side of the equation and I'm going to rewrite it as just log of 2x times x minus 5 equals 2. So what do you think of that? Yes, it's right. Remember that the addition of logs is the same as the product of the numbers, or the multiplication of the numbers. Now we can solve this very much like we did for example 3. But again, what am I going to do here is I'm going to add a log. Remember that log is just log base 10. So I'm just going to go log base 10 of 10. That's equal to 1. All right, we're getting closer to the solution here. And we're going to take that 2, of course, as per our trick here, and we're going to move it on to the 10. So now we've got this rewritten as log base 10 of 2, property of logarithms, right? And this is log base 10, and let's go ahead and multiply it out. 2x squared minus 10x. Okay, all right, so believe it or not, as crazy as that looks, it all comes down to just becoming 2x squared minus 10x equals 10 squared, which is the same as 100, right? 100. Now you're probably going, I forgot how to solve these, but let's not think that. This is a quadratic, so what we're going to do is we're going to put everything, we're going to set it equal to 0, and by subtracting 100 from both sides, see if this all comes back to you. And let me go ahead and make some more space for us over here. Now I have 2x squared minus 10x minus 100 equals 0. Who said that you can divide everything here by 2? Oh, okay, that was good. I can't figure out who that was, but I guess you all shouted it out. But if I divide everything here by 2, which is totally legal, all right, notice that the garbage disposal on the right hand side takes care of that, takes care of the 2. I get x squared minus 5x minus 50 equals 0. Two numbers that multiply to negative 50 and add up to negative 5. Any thoughts, anyone? How about 10 and 5? Does that sound good? Like minus 10 and positive 5? All right, so that means that x minus 10 equals 0, and x plus 5 must equal 0. Add 10 to both sides, x equals 10. and subtract 5 from both sides. Now you be careful of these negative numbers because they may be extraneous. So if we go, for instance, and take that -5 and we put it in the original equation, all right, look at this. If I put it in the original equation, what does that -5 do to that log of 2x? Well, it makes it log of -10, which is not something we're allowed to do. So the answer is only x equals 10. Let's do these next two sample problems, and we'll call it quits. So, ready. I'll start you off. Left side is going to be log of 5x times x minus 1. And on the right side, okay, so addition of the logs is the product of the numbers. And on this side, I'm going to write this as 2 log base 10 of 10. All right, just multiplied it by 1. Log base 10 of 10 equals 1. But, of course, doing that allows me to put the 2 up there as an exponent. All right? So now I've got log base 5x of x minus 1 times x minus 1. Oh, I should have multiplied it out. Equals log 10 squared. Okay, so now let's go ahead and multiply it out. 5x squared minus 5x equals 100. Right? Just remove the logs because what's inside the logs is equal to each other. Therefore, what's inside the logs must be equal. Exactly. Okay, so let's subtract your 100 from both sides. 5x squared minus 5x minus 100 equals 0. Oh, you're right. Everything is divisible by 5x squared minus x minus 20 equals 0. Now two numbers that add up to multiply to -20 add up to -1. You can do it. Okay, -5, +4. So we're going to get another two numbers here. We get two answers here. So there's the possibility for an extraneous root. And x plus 4 equals 0. Add 5. X equals 5. And minus 4. X equals -4. And of course, the chance of getting a negative, an extraneous root from the -4. Let's go ahead and check up here. I see the problem already. It's right here, right? 5 times -4 is -20. I can't log a negative number. In addition, if I put the -4 in here, I get -4 minus 1 is -5. So I can't, again, I get another logging a negative number again. So that can't work. So we only get one answer. All right. I am going to challenge you to see if you can figure out how to do number 8. And so go ahead and pause, and then I'll do number 8. You can check, see how you did. If you were successful there, you pretty much got an A for the day. So give it a shot. Oh, and let me make sure you can see the one I just did so you can be guided by it. Okay, here we go. Final answer is just x equals 16. If you got that, if you did that, you're awesome. You had a great day. If you didn't, just look back and look at the work, see how I did this again, all right? Again, what I did is I put in that scarecrow log base 4 of 4. That's starting off at the beginning, right? Is adding the logs is the same as multiplying the numbers. So I got x plus 12 times x equals, and then I put in the dummy log 4 log 4 of 4. And in my next line here, I distribute the x, get x squared plus 12, and I put the exponent, the 3, above the 4, so I get 4 to the third, which is 64, by the way. So now I can remove the log base 4s because they're now equal. X squared minus 12 equals 64. I subtract 64 from both sides, and it just happens that I was a getting all the ways of multiplying to get 64, and when I wrote 416, I go, that's it. So x minus 16 times x plus 4 equals 0. That leaves me with, eventually leaves me with 2 roots. The x equals negative 4 is not a good root. So we'll erase it, and the answer is x equals 16. Well, anyway, hope that worked for you guys. If you need to, play it back and go ahead and practice it again. If you get a chance to go ahead and take a look at the homework right now, you can do that. But otherwise, I've reserved most of our next session, our next meet session, to go over this work. So until next time, you guys take care. Have a great day. Bye now.